So we have Neil and Chris, who are both developers at Meta, programmers at Meta, and they built the Buck2 build system. This is one of the remote execution API compliant build systems. So take it away.
Thank you. I'm Neil. This is Chris. We are both at Meta. So there were many of us at Meta as part of it. We're the two here, but like team of 30, over many years. So cool. So for this room, I would say Buck2 is kind of a bit like Bazel in some ways, and it has its own unique idiosyncrasies and improvements, we think. But it is a build system. It was developed at Meta. So Meta developed Buck1 maybe 15 years ago. It's quite a while. 10 years ago. Open sourced it. And then 4.5 years ago, roughly, we started working on Buck2, which is the successor to Buck1. So aiming to be much better, but still mostly compatible with Buck1, so we could actually get that. As of today, it is the majority for the backend services and lots of other stuff at Meta. Meta is a kind of polyglot company. Basically, if you can think of a programming language, there's some production code using it. So we support languages like C++, Rust, Python, Go, but also things like OCaml, Erlang that maybe aren't as well supported in some other build systems. It's designed for large monorepos because we have a large monorepo. It's open source, so there's both the website and the GitHub repo. And pretty cool, it is twice as fast as Buck1 in the benchmarks we've done. And that's benchmarks on real user code or real user experience. So what's the architecture of Buck1? Well, let's start on the far right. You have a targets file written in Starlark that makes calls to various rules, exactly like Bazel. Then you have the rules, again, written in Starlark. And these will typically define a library, a binary, and a test, and it will support C++, Python, blah, 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 much like Bazel. Perhaps the big difference is all of our rules are written in Starlark. We have absolutely no rules in the core. The core has absolutely no knowledge of any programming language, which is really cool. And there are also rules for things like download, shell, commands, aliases, all the things you might expect. Perhaps the biggest difference to Bazel, well, we have a different rule API with different features, different power to weight ratio. We also have static type checking, which is kind of handy. And then we have the core, which is written in Rust. So this is where the build graph lives. It's where the APIs live. We spend a lot of time on our Starlark interpreter, which is also available as a separate open source library, but features like profiling, LSP, IDE integration, linter, type checker, all the good stuff. Where the console output lives, we also have a separate library called superconsole for that you can use independently. Logging, events, performance, all the good stuff. And then we connect these things with the API to the rules. So I said it was twice as fast as Buck1, and that's pretty cool. Like, we really do mean for developers internally to Meta, if they were spending 10 minutes doing something with Buck1, they're now probably spending more like 5 minutes doing it with Buck2. So that's pretty good. And we were able to even prove that developers whose builds were sped up by Buck2 actually produced meaningfully more code. So it isn't just like, well, now that you're spending less time compiling, you're spending more time, at lunch or having meetings. You're actually spending more time being productive, writing more code. Yeah, not a surprise result, but nice we're able to prove it statistically. How do we get this performance? Well, the abstraction is very important. We only have the rules. The rules only talk through a very narrow API. So we've been able to redo various functions in the compiler, like the write file. Does it write directly to the CAS? Does it write to a temporary file? Does it store it in memory? Does it compress it? All these things we've been able to change around and play with to tune the system. There's a single dependency graph. So I think there's a proposal in Bazel to merge the analysis and action graphs. We've always had a single dependency graph that includes the Starlark and everything from day one. Remote execution. We knew we were doing remote execution from day one. So everything flows around the compiler as pre-computed Merkle trees with Blake3, so it's nice and fast and there's no impedance mismatch from our execution. We have deferred materialization, which is our name for building without the bytes. Again, from day one, we have virtual file system for input files, which you don't have to use, but is there. Rust, so there's no GC on our nice big graph, which is kind of useful. And we've just been very careful to keep with the performance. So the good is we think this is a powerful, modern, well-developed build system. It's actively developed by us and others. And it's very much open source. So if I land a diff, it will go upstream to the GitHub repo in about 15 minutes with the commit message and everything. We accept PRs, and it's basically the identical thing to our internal version, minus the remote execution server. Because we have a remote execution server that uses our internal systems, which obviously aren't open source. So for the open source version, it is switched to use the remote execution cloud. And I think Andreas did that. Yes, and others. The bad, changing build system is hard. So if you're using a build system and you're thinking, should I change build system? This will be fun. No, it won't be. It's new, so there's only a few external users, so it works. We have a CI testing it externally, but you're going to run into teething troubles. While we've open sourced the rules for things like Java and Android and iOS, they don't really work yet. There are some tools that maybe aren't as open source. We're working on that, but take a little bit of time. And the whole package, workspace, dependency, external dependency story that Bazel has, we don't really have any of that yet. But we probably will do one day. So one of the really big features that Buck2 has that maybe is lacking in most other build systems of this scale is that we are slightly dynamic. What do I mean by that? So a dynamic dependency is the idea that you don't have a static graph that is constructed when you parse all your Bazel files or your Buck files or whatever, but there is aspects of the graph that are constructed at runtime while things are going. So think of where this would be useful. So for distributed thin LTO, you call the linker and it spits out a JSON file saying what files should be grouped in what way. You really want that information to be on your graph, but you can't get that information statically. You have to compile all the files first. So you want it slightly dynamic. Another example, OCaml compilation. You want to compile everything in the OCaml library, but you have to do it in dependency order within the library. So you could have the user write out the dependency information, which is say what Bazel does, or you can ask the compiler what's the right order to compile it in. And again, you can do this way. But there are some build systems that are entirely dynamic, like shake and redo. But if you go that way, what do you build on CI? So in CI, a standard way in kind of big scale CI is you basically list out all the targets and all the dependencies, figure out what targets have changed, figure out the blast radius, some distance, and compile that to check. If you're able to add arbitrary dependencies at runtime, then maybe you're going to miss something. And that would be terrible. And you can't build the whole world to compute this graph. So it has to be somewhat static, somewhat cheaper to compute. So the solution to this is we've added two types of dependencies, dynamic outputs to extend the action graph, and anonymous targets to define the graph that give us the power to express these dynamic things without losing the CI properties. I'll hand over to Chris.
Great. And I'll talk about those two, and then the slides that Neil skipped over. Great. So dynamic outputs first. Right. As Neil was talking about, most build APIs require you to construct this static action graph. And so you can't create new actions after doing things like run linkers or running external commands, right? You need the action graph to be fully defined in the build files. And we encountered several of these issues, and we're trying to figure out a way to resolve this. And so the solution to this problem that we came up with was what we call dynamic outputs. And so I imagine most people here are more familiar with Bazel than Buck, but it's going to be similar. So we have an analysis phase where we run rule implementations. And during that time, normally you declare artifacts and then bind them to actions, right? With dynamic outputs, you can bind an artifact to a dynamic output. A dynamic output is just a Starlark lambda, similar to a rule function, that once we require that output, we'll run that lambda. That lambda has, it declares some artifact inputs that we will first build and then make the contents of those artifacts available to that Starlark code. That Starlark code can then do the same things that normal analysis could do. It can declare new artifacts. It can bind those to new actions. It can bind those to new dynamic outputs. Yeah, and let's see. It's an example. I'm not going to go through, all the details here. I imagine this looks somewhat similar to a rule implementation in Bazel, though I've never written one. But so, what's going on here? This is just a very simple thing. Declares some output, and you see the sort of def f in the middle. That's going to be the Starlark function that you can see later down is bound to the dynamic output. It actually reads the lines of its input and then does something based on this. I believe, this example is filtering inputs, right? I think Bazel does this for C++. I think Bazel has some internal functionality for input filtering. But this would be an example of how you could use dynamic outputs to sort of filter a large list of inputs down to the few that you need. Imagine maybe you could do that computation locally very quickly and then send a smaller action to remote execution via that filtering. Great, I think. Great, some of the real life examples, actually Neil hit on these in the previous slide, right? So distributed thin LTO is kind of this picture here, where those dotted lines are the ones that we can't figure out until we run an action that had looked at sort of the bit code outputs from the compilations. And then we can define the optimizations, the optimization nodes by this dynamic output. I know camel depths you'll also hit on, and I won't really go over it. Great. So anonymous targets is the other one that Neil had mentioned. This is an interesting one. When you look at the target graph and the rules, right? You have everything. You have, I don't know. You look at the target graph, right? You have C++ library. It can introduce that. There are cases where we don't know the structure of what we need at a target until later on, until the binary level. A great example of this, I believe, is down here in Swift modules, where we need to know how the dependent of the Swift module wants the flags to be able to compile the Swift modules of its dependencies. So the solution is this non-target, and that's a target node that's defined by the hash of its attributes. It doesn't have a name. Within analysis, if you can construct these attributes, you can create one of these nodes. I think maybe looking at an example will maybe make this clearer. Right. So again, you have on the lower side, you have this inflow function for a sort of normal rule. And you can see where it calls this a non-target. And it just passes in a non-target rule and the attributes that's going to pass to it. An interesting thing here is it's not static, right? This returns a promise in Starlark, and then you can map on it. Maybe if I go back, there's this interesting thing. Talk about aspects overlays here. So for a couple years with Buck2, when we were going, we had this, I don't know about a joke, but we said overlays would be the problem to this category of issues. And we never really knew what that meant. In our heads, it was like aspects from Bazel. We didn't know. Eventually, we came up with this in non-targets and realized that would solve our problems. Something like Python native library sharing is an interesting one. So here is Buck does this thing called omnibus or native Python, where we know the links for a Python binary only at the binary level. With Buck1 or Buck2 early on, This meant that no Python binaries could share those link nodes because we only knew what we needed at the binary level. With the non-targets, if multiple binaries create the same non-target, that will be shared. So, great. Let's go back to fat platforms. And we have about 2 minutes. Okay. I'll try to get through this quick because I want to leave some time for questions. Fat platforms is an interesting one in the context of RE. So what am I talking about here? The problem is we have a bunch of developers on Macs, a bunch on Linux, and by default, the way you construct a build, even if you're using RE or caching, the Mac and Linux are like separate things, right? You send your Mac actions to Mac RE, you send your Linux actions to Linux RE. This is the problems that like for us, Mac RE is really expensive. I imagine, right? I don't want to speak for others. Maybe they've solved this problem, but for us, that's really expensive. We also then you have cache duplication, etc. I throw a bad solution on here, right? We could run everything on Linux RE and use Linux caching, which would kind of solve it for Mac, except then they can't run things locally. And for developers, we know that like for Buck2 at least, it's very important for performance to be able to run things locally when there's not like high fan out that needs RE. So our solution to this has been to use what we call fat platforms and fat tools. So a fat tool is just a tool that can run on multiple platforms. Some things naturally support this. Some things naturally support this, say Java, Python, tend to naturally support running on multiple platforms. Other things don't. Typically, our solution for those is to just build multiple of them, put them together in one tool, and select which one to run at runtime. And then we have fat platforms, which would be a platform that represents something that could be Mac or could be Linux. And then for RE, we always send that to Linux, but it could run locally as Mac or Linux. Great. As an example, the very first thing we did in this way with RE at Facebook was the Android NDK, which comes with binaries for multiple platforms, and we wrap that into a fat tool. Let's see. I'm just trying to. Yeah. Great. So yeah, with this, what we found is we can define actions that we can run on Linux RE. Locally, users can run locally on Mac. They can share cache between Mac and Linux. And yeah, the biggest downside is that these fat tools are much larger than their non-fat counterparts. For the most part, we limit it to two platforms, Mac and Linux. We haven't really explored Windows, Mac, Linux, something else, ARM plus x86. But even with just Mac and Linux, we found we need to avoid some of that cost of the fat tools. And so we do have some mechanisms internally to kind of limit that.
Are there special features in Buck2 that enable fat platforms, or is this just a way that you're leveraging Buck2 internally?
Yeah. Are there special features? Okay, so again, we compare a lot to Bazel. I don't know the details of Bazel to speak to that. For Buck2, this is mostly a fact that execution platforms. So Buck2 has a feature called execution platforms. In this, you define where it can run locally and what remote execution sort of properties to use to select the remote execution. You then declare a whole bunch of these execution platforms as the possibilities for each target. So each target then resolves to one of these execution platforms based on its execution depths. And then we have target compatibility. So most of our tools are incompatible with something about the fat platform. And then a fat tool doesn't have that incompatibility, which allows us to select a fat platform for it. So Bazel has a lot of these same concepts, right? I don't know how they fit together in the same way. So yeah, it's just leveraging some of those that configurability of Buck2.
Bazel versus Buck2 could be a hands-on discussion here.
I mean, I'm pretty sure
Now the
Andreas
next
is
talk
coming up next to
comparing Bazel and Buck2.
yeah,
Alright.
yeah.
The Bazel can actually provide, I think, a JVM type tool for Bazel.
Okay.
And the reason it works with Bazel is not because it's particularly smart, but because it's particularly dumb. It doesn't actually check that the platform that you have specified in Bazel and the machine you're running on, that they actually match. So it will just try to run it, and then, if it works, then it works.
So in this case, it's solve the execution gap, and instead of just being done and running it.
Yeah, and you could have multiple flat platforms and it would pick the right flat platform. So yeah, I would say the constraints were designed with us knowing that we wanted this in mind, but we didn't do anything specific for this.
So one more question. How's your Windows?
It works on Windows. Like I do it. I do my open source development for Buck2 on Windows. Works fine.
I mean, we have significant internal usage of Windows at Meta, right? And so Windows is an important platform for Buck2. Similar to say Android and iOS, maybe the open source is it's not quite in that state yet.
I mean, I think for Windows it mostly, it mostly actually is there. It's the Android and iOS that are lagging a little bit more in the open source because I do my open source hacking on Windows. Right.
Any other questions? Yeah.
And right in the beginning, what did it mean? What did you mean by meaningfully more code? How did you measure that? Because
So I would love to go into all the details, but that's the bit that that's the approved statement. So developers who switched to Buck2, they produced more output, more diffs, more code.
Is that good or bad?
I mean,
Both.
there are ways to cause developers to produce less code that are easy, and I think everyone is searching for ways to get them to produce more code. The meaning for the amount and the curve, that's all. I actually don't know the details of that, I'm afraid.
All right. Thank you.
Thank you.